Now, folks, we're following on from last week. You can turn on your remotes again. No. So our second session on forces. Last week we did a quick survey of the different kinds of simple machines. Simple machines, the slope or wedge, the mechanical screw, the wheel and axle, and beam, and then from those you get things like levers, gears, and pulleys. They're kind of simple machines as well, but they're adaptations of the other ones. Okay. Now in the real world, these are used in equipment and machinery and in items that we use. Okay. You see up here we've got gears from bicycle. Okay. And a gear wheel is just a wheel with teeth on it. Down here we've got various kinds of pliers and clippers and so on. What about this lifter, the blue lifter? What do you think that is? Which of the machines is it? Is it levers? You think so? Yeah, it's actually quite a few levers. Each one of those rods, okay, it turns at 2 points. Each one of those components is a lever, so you've got quite a lot of them. You just add up all those different little beams there, and that'll tell you how many levers you've got. In this large crane, it's a beam going across there, horizontal beam, but it's going to have lots of other parts like this, and these are pulley wheels. Okay, and here where the cursor is, you've got a very simple pulley, very simple one, and here we've got what's called a compound or complicated one, right, with lots of wheels in there. Okay, I haven't added them up, but I think there's about 8 or so. Right. Now, looking ahead, something else we might get time to do is to look at things that are involved in these down here at the bottom, excavators and JCBs. All right. Now they're complicated in the sense that they're made up of many different machines combined together. Right. Now, do you see this thing going at the top? Now you see these on JCBs and excavators, and what it is, you got this steel rod which goes inside a cylinder, and it has then this black tube which runs down back to the machine here. Okay, what's in there is not just a machine to an engine to make the machine move forward, but it's also a compressor, and it compresses and compresses and compresses liquid in those black lines that you see. You can see these black tubes going all over the place in these machines, and inside there's a liquid, and it's compressed. Now when you have that as a way of moving something, it's called hydraulics. Hydraulics. The other one that doesn't use a liquid but uses a gas is called pneumatics, beginning with a P. Okay, Greek word. It's pneumatics, right? And we can actually simulate those very easy in the lab just by using plastic tubing and some medical syringes, and we can make it hydraulic just by putting liquid in it, or gas just by leaving air. Okay, so we can play with those another day. All right. Now, what we're going to look at today is, well, if we were transformed ourselves 100 years ago in this very building, we would be studying a thing called Hooke's law. And there are pictures from a textbook from the 1930s, right, showing how it could be done, the setup and so on. But today we're going to have a look at Hooke's law, but not by kind of calling it that. All right. So if you did this before, you might have done it in secondary school. You may have done it even in Leaving Cert Physics, but we're not going to talk about laws and so on. We're more interested in what's called the phenomenon. All right, that this is to do with, and the phenomenon that it's to do with is elasticity. All right, elasticity. And what does that mean? What is you think elasticity to do with? What do you think? Elasticity. Stretching. All right. Now, it's a material is elastic if it stretches. And what's the second part? It always returns to its original shape and size. Okay. Now, if a material stretches or bends or changes shape, but does not spring back into its original shape or size, you don't say it's elastic, you say it's plastic. Now, in science, we use those words differently than we do in everyday life. We're more specific. In everyday life, elastic is a noun. In science, it's an adjective. In everyday life, plastic is a noun usually. We talk about plastics and recycling our plastics and so on. But in science, it is definitely a noun. Sorry, an adjective. It describes a phenomenon. Okay? So elastic, if it can stretch it or bend it and it'll spring back to its original shape and size. Plastic, if it doesn't. Do the second part. Okay. So what the pictures show is, in the first one, you have weights hanging on a spring with some kind of measuring device there. In this one, instead of the spring, you've got a piece of material, say a piece of rubber strip. Okay, and they're hanging weights on it, and again they've got a little, it looks like a ruler hanging on the side and measuring the length of it. So we've got our elastic materials here, and I've got two types. Okay, I've got elastic bands and I've got springs. Okay, so that's our elastic materials that we'll do our experiment with. So I want to just go over some key words first. All right. So try and answer this, whatever you think. Okay. Try and answer this using the clickers, folks. 30 seconds. Which one is the fish? Is it the load, the tension, the extension, the stress, and the strain? Turn it on. Turn it on again. Hmm? Well, some. We may do it again. Does it help? Doesn't matter. Okay. There are two answers anyway. Oh yeah, I'm finding trouble with this thing. Right, load. These are all words that we use in everyday life, but they're in science they tend to use them a bit more specific. Okay. Now here's the thing: some of them mean the same as something else. Okay. Some of them are just synonyms. So we go to the answer. Well, load is the weight on the spring, so that could be the fish. Okay. Now, specifically, the strain is the force of that. That's of of the load. Okay, but what is experienced in the spring is called the stress or the tension. So stress and tension are the same. Stress and tension, and load and strain. Now, depending on what book or website you look at, if you're ever doing this, they will use different words. So it's just kind of important to know which ones mean the same thing, because they mightn't explain it, you see. Now, the extension is the change in length. The spring gets longer when you hang something on it. Okay? So the new length, the extra bit, is called the extension. Now here's a question. See, can you get this? Yeah. All right. You have to type in the letter here. It's A or B. And does this graph tell us there's a connection between the load and the extension, or there isn't a connection between the load and the extension? Is there a connection, or isn't there? Now I'm sort of messing with your minds here, so don't worry about it. Okay? Because the fact of the matter is, there is and there isn't. Okay? Both answers are right. There is or there is, and there isn't. There is a connection in this part of the graph. And that tells you, that's a key, kind of a key thing whenever you're getting children to draw little line graphs. When you have a line, it means there's a connection between the two things. Okay? If the line starts from the origin and moves up across in that direction, it means it's a positive connection. One thing increases, the other one increases. Okay? That's what that means. If the graph started up here and worked down, it means that as one thing increases, the other thing decreases. That's a negative connection. However, when you are up here, it's not a clear-cut thing at all. Okay? The thing starts to unravel a bit. Right? There's some kind of connection, but it's not a direct one. Okay? Now, instead of connection, in science, they use the word, does anybody know? That's it, relationship. Okay? And I know some of you are going to go, some of the lads particularly going, oh, does this mean commitment? And yeah, in a way, but the word connection might be easier, all right? So, there is a direct positive relationship between the stress and the strain until the plastic region is reached. According to this graph. I want you now to design your own experiment to find out if there really is a connection between the stress and strain. And record your results on a computer and draw a graph of the results. Do you have computers with you? Yes or no? This means yes. This means no. Unlike in Greece, where this can mean no. No, really. You know computers, no? If you have a laptop with you, use it. And if you don't, we use these. Okay? And we share them to a bench. Very well. Okay? You put them back at the end and so you don't need can you take everything else off the bench? You don't need pens and paper. Two for numbers in the spreadsheet. Okay, folks, have a look. Numbers is the program we're using. It's a nicer program than Excel from the point of view of usability. So we open it up. Okay. Now. Okay, folks. Now, what you can do is you enter the numbers in a vertical order, not across the way. So let's say your initial length of the length of your spring is going to be 25 centimeters, and then, but that's with no weight. Then with 100 grams, it becomes, well, actually it's still 25. It hasn't moved. And then it's 26.5 for 200. And then 28 to 300. Okay, let's say that's your way you enter your results then, all right? Then to draw a chart, click down there. Sorry, did you see? Under charts, click down there, and you're going to go for a line graph. And that looks like false reading. So let's just do that the other way around. No, that's three grams. It's plotting length against weight. No. Okay. Right, have a look. Have a look, folks, up at the overhead so you know how to enter the results and to make a graph. Now, I have produced 3 graphs. One is the proper graph for, say, 5th and 6th class. One is a graph for 3rd and 4th class, and one is an incorrect graph. Now, one is totally incorrect. Now, look what I've got up here. All right. Now, the way numbers works is in the grey column, you put the variable, the thing that's changing, but the one that you're affecting. And in the other one, you're supposed to put the thing that comes out of it changes, the output variable it's called. Okay? So what I did, I decided, well, or by accident, I did the wrong one first, okay, as opposed to later. And I put my measurements, and then I said, oh, I should put in the weights, okay, which is the wrong way around to do anything like that. All right? So, so you highlight the thing you're going to make a chart of, and you click chart, and then the type of chart you want, and what comes up is this thing down here, okay, and it's a perfectly straight line. Wonderful. Okay, of course it's a perfectly straight line because it's really just showing how the weight increased as the spring got longer. Do you see what's wrong with that? I say it again. The graph shows how the weight increased as the spring got longer. Okay, it's the other way around, isn't it? Okay, that's why the graph's wrong. All right, it should be the other way around. So that one is wrong. We delete that. Okay, now we have these 2 graphs, and they're both correct, but they're very different. Okay, can you see what the difference between them is? They're actually the same results, so they are. All right, now there's the measurements for my spring. Okay, it stayed 25 centimeters is the length of the spring. It stayed at 25 even though there was 100 grams on it. It then went up to 26.5, 28, and 29.5. Okay, so again you would get your chart and you click on that, and if you just use the raw data as is, you will get this chart. Okay, you will get this one. You get that one because in each measurement is, as it were, the overall original length of the spring anyway. Okay, you're starting off, you know, at 25 centimeters always, like that. Now you've 2 options. One, you can get the computer to subtract out the 25 centimeters and just start your chart at, say, 20. You could do that, and that's an IT problem or a mathematics problem or whatever, okay, or a mathematics solution to it. But the sciencey solution to it is actually, let's see now, let's think. Because what we really are interested in is extension, not necessarily the overall length of the spring. So here we have the extension. Now the spring with no weight has no extension. The spring with 100 grams here didn't increase in size. It still was 0. And then where did that 1.5 come from now? Where's that number come out of? It's 26.5. Take away the original length of the spring. So you subtract that out, and it allows you to forget about the original length of the spring, and you're only getting the extra bit each time. So you plot only that piece of information the normal way, and you get this graph. And what you see is that it begins at the origin. So it does. It begins at the origin. All right? No weight, no extension. All right? But 100 grams, you still get no extension. Why is that? In the spring eye we happen to be using. Why was that? What did you notice about your springs? They were all different. Okay? Some of the springs are really what I call soft, in that you could put 10 grams and they extend. Some of the springs are really tough. Okay? And they need about 200 or 300 grams before they start extending at all. Okay? So that's why in this particular one you get ones, they don't begin to have any extension until there's a good substantial weight on them, like 200 grams. Okay? Now, this is a perfect straight line. How did you do? That's because they're made up results, by the way. Okay? You don't often get perfect results. So what I want you to do, I want you to try and produce a graph like I've showed you now, and we'll see, can you produce a graph and see is it nearly a straight line?